This time I'm going to talk about the most practical issue, how to deal with real data in the field, or measured in the field. I don't know how many of us have experience with real data. That's always too noisy. To support my research addiction, I have made a lot of field work trying to predict lives in many structures. And sometimes you go to the field and bond strain gauges and measure history during some time, 1 hour, 2 hours, whatever, to get representative data. And this signal comes with a lot of non-damage events and too many peaks and valleys due to noise. And if you try to work with that in order to make fatigue life predictions considering all the features of the measured events, there is no computer code that's going to be able to deal with that. So let's start saying that's the most important practical issue in fatigue analysis, and even more when we are dealing with multi-axial problems due to the complexity of the damage accounting, is how to properly filter a variable amplitude load history to decrease the intrinsically very high increase of multi-axial computational costs. In multi-axial histories, like in the 1D case, the first idea that can come to our mind is to filter all the events that are not peak or valleys. When you go to the field with a digital system to measure data, we have to oversample the data in order to get all the features, at least at a frequency twice the maximum frequency of the signal, but frequently at least 10 times as fast to not distort the signal. In multi-axial data, it's very easy to get rid of most events. Just consider peak and valleys and forget about the depth, even before filtering the amplitude. However, we cannot do that in multi-axial analysis because the path between load reversals is needed to evaluate the path equivalent of stress strain associated with rainfall, with each rainfall counting. For example, using an convex enclosure method or the Moy method our group prefers. The reversal points obtained from a rainflow algorithm might not occur at the reversals of one of the stress strain components. That's the most important point. Of course, we all know, or should know, the Uniaxial Racetrack filter that's so much useful in Uniaxial histories. The idea has been proposed a very long time ago by Professor Fuchs that he was himself a skillful skier. And skiing downhill, he had the idea to filter out the events that had not a major amplitude. I guess we all are familiar with that, but that idea was very interesting from the fatigue point of view. Conceptually, it's completely different from the frequency filters we're normally using to deal with noise histories. We do not filter in frequency because if you try to do so, you are going to distort the signal, and that's the most important feature for fatigue analysis. The multi-axial, the uniaxial rainflow, the Racetrack filter, can be also seen as analogous to a pack that oscillates inside a slot. It is exactly the same thing as the Racetrack itself. And this way of looking at the Racetrack filter is much more useful to generalizing it to the multi-axial case. So, in multi-axial filter objectives, like in uniaxial case, is to eliminate the unavoidable noise of real signals, and as well as the small load events that do not cause fatigue damage. We don't need to analyze the small load events that are below the fatigue limit. It's very simple to understand that in the uniaxial case, in the multiaxial case, a little bit more difficult. If you try to use the Peaks procedure, I said before, removes all data points that are not peaks or valleys, we can have a trouble when analyzing the signal. Because if you get a signal like the diamond one or the circle one, if you try to remove just all points between extremes, we are going to have a huge problem, because the damage induced by this kind of load history is different from the damage induced by this kind of load history. The path does matter in multiaxial fatigue. This is another example that illustrates that. If you have a load history like this, and both get rid of all the events between the peaks, you simply don't get the maximum damaging event. That's a major issue in multiaxial filtering. Moreover, if you do have a real signal, a noisy signal, for example, this is what we, in fact, measure in the field. A baseline signal with a lot of noise. If you try to get rid of all peaks and valleys, we're not getting rid of anything in the signal whatsoever, because every event is either a peak or a valley. So the issue is not that trivial to start with. So the idea of the multiaxial racetrack filter that has been introduced in last MPT, where is to use the pen analogy in multi-dimensions. For example, in a 2D history, instead of working with a slot, we are going to work with a circular hole. That can be generalized to a hypersphere, in general 6D histories, or even more complex histories when we do a lot of signals. And can make this hypersphere translate in a Mises space with a radius r equal to the required filter amplitude. So the load history is represented in general in a 6D space. Of course, we have to use 2D space in order to visualize here in slides. And the amplitude must be chosen in a way to remove every event that don't need to be accounted without removing any event that can cause real damage. So this no peg is then allowed to move inside the CD space, but kept inside the CD hypersphere that has a center O in an instant and the radius R that is used to remove the noise. When the peg reaches the hypersphere, the surface, and tries to move out of it, both the peg and the hypersphere translate all together. And you can filter the points in two ways. One that's dynamically filtered when the sphere is moving and the points that the sphere is looking that are inside it are filtered from the signal, or statically, where you have events inside the sphere that are below the limit we have set. So we call that static filtering. If we remove those events from the signal, supposedly we are going to get with the same account of damage, but without having to make a lot of unnecessary calculations. Moreover, another way to understand how the racetrack filter works is to use its directly analogy to plasticity. We can think in a multiaxial racetrack filter inspiration based in incremental plasticity. The filter cycle, or the hypersphere cycle, is analogous to a yield surface. The filter amplitude is analogous to the yield strength, surface radius. Dynamic filter is analogous to plastic increments with elastic variations. Static filtering is a purely elastic increment using the yield surface sphere, if you want. And the filter reversal is analogous to a load reversal, a large change in plastic direction. So if you're a user to play with plasticity, this filter analogy is another way to understand what is happening. Moreover, even though those ideas are not that trivial, the implementation of the filter in a code is not that difficult, because those simple rules can be easily programmed. My partner, Marco Mediolaro, is an outstanding programmer. So every time he sits down to make a program, he says that's easy to do. It is easy for him, not for me. I'm a stupid guy. I don't know how to do that. So I did agree with him that not only we are going to present the fluxogram of the code in the paper, but we are going to introduce as well the code itself to share it with the community. We think that's so interesting to use it that we are going to give the code to anyone that wants to use it. So all the movements of the hyperspheres are inside this fluxogram, but they will be in the code as well. Let's see what a multiaxial racetrack filter can do in a 2D load history. If you have a very complex load history with a lot of events, some of them large, some of them very small, it's sensible to choose a filter amplitude in order to remove the small events before doing the damage calculation. But what are the two features we want to maintain? We want to remove all the events that make no damage whatsoever, but we cannot remove any event that causes damage. So how to visualize the figure? This figure is a little bit too crowded, but I guess we can play with it. We have an original history, and you can initially choose a size for the filter. And you can use two ideas when choosing this size for the filter. The first one, if you are very good in damage calculations, have a lot of experience, we can guess a size for the filter that's suitable to remove all non-damage effects. However, in practice, if the code is fast enough, we can do a try-and-error procedure. We just choose a size for the filter, start with a large one, make damage calculations, a very small number of events. Then we can choose a smaller size for the filter, do the damage calculation again, and when the damage calculation converges, like in all finite element codes, we can say we got the right size for the filter. I myself am used to do that. I have done that many times with real-time histories, measuring the field when I try to use them to make epsilon n calculations. Epsilon n calculations, SN calculations are too easy. However, epsilon n calculations must be done in a sequential way. And if you try to do this in a real history with 20,000 events. We are going to take a long time making computations. If we filter the history before, it has happened to me. You get a 20,000 event load history, set a real decent size for the filter, and the histories come down to, say, 5 events. We can even calculate it by hand. So this filter, if you can play efficiently with the size of the hypersphere, is a real engineering tool. And here we can see what happens. When we have a huge radius for this sphere, we remove a lot of events from the regional history. When we decrease the radius, we increase the number of events. That gives us a feeling what an amplitude filter really is in practice. Well, that idea has been presented before in Rubin when we introduced the filter. However, why I'm presenting this once again? Because we had another idea, how to optimize the filter performance. And to optimize it, to make it much faster, we had an idea of introducing a partitioning pre-processing. Now, I guess, we get the filter routine as fast as we can get. We have no other idea how to improve it. The idea is pick up the starting point and the end point of the history, and then in sequential try to find in load history the most distant point between the connections between the start and the ending point. I'm just illustrating here how to do that. I'm going to show in the next slide how this works, and I hope everything goes well. Starting the end point, most distant point, then subdivide the history, and in a few steps find the most distant points. We can get points distributed in a very fast way in a code before doing the racetrack filtering next. For example, this history is a little bit more interesting. We have a history, more or less a square one, with some events that are either small or larger, and a lot of points between them. If you just imagine small variations between the points when we measure them in the filter, and we are going to consider all the events of this history, there is no computer time possible to make real damage calculations in practice. We are all engineers. If in order to calculate the damage from this load history, we are going to take, say, 3 days in a computer, no way this is going to be a practical tool. So the idea is to remove from this load history all the events that are either clearly noise, unavoidable noise. No one here that has ever bonded a strain gauge or used any other experimental device can get rid from the noise. It's impossible. So the small noise is nothing. Get out from the noise. And also, why analyze the events that goes on damage? We don't need that. So let's go to see how this happens in practice. Starting the end point of load history, most distant point, most distant points from the load history. In a hurry, we can get the overall shape of the history. Then we do the racetrack filter to consider the events that can cause damage. So initially you had a history with 488 points that come from the digital measuring system, and the damage calculated using on 11 points is exactly equal to the damage we would get calculating 488. However, the time to do that would be just a small fraction of the time needed to analyze the entire history. I do believe that is the most practical tool. And this idea, that's extremely simple for us, is not that simple for real engineers. In fact, we get the inspiration to do this filter from a questioning from the aeronautic industry in Brazil. Some friends of ours went to the university and asked us a question that they didn't know even how to ask the question. It was interesting. They were testing engineers using maybe 8 load channels in an airframe to input load. Imagine a huge airframe with 80 hydraulic jacks and measuring the data of all the jacks at the same time. And they asked us, we get a huge amount of data, and we would like to condense the data in order to analyze the results. How do we do that? This idea can be generalized to any number of channels. And we told them, be extremely careful when you think in filtering signals. Because if you get a filter in one load signal without considering the others, you are going to lose the sequence information. And they haven't not realized that because they are not that well trained in understanding how this works. Here is another load history. 300 points. Too many points to be analyzed. We don't need to do that. Look. Oops. Go ahead, my lord. I guess I'm a lucky guy. 3 of the, the systems work, and I don't know what's happening with this one. Ah! The pre-partitioning sequence, that's extremely easy to program because we don't need to have the hypersphere movements, was enough in this case to do the filtering completely. We didn't need to use the Racetrack filter after that to get the real system. As a last example, complex load history. Pre-partitioning, starting. Extremely easy to get all important load events. So, conclusions. This improvement we are presenting today in multiaxial Racetrack filter is a very efficient amplitude filter that's applicable to all multiaxial histories and to fatigue damage models based either on invariant or on the critical plane approach. This filtering is able to filter all low amplitude events due to noise or to non-damage events, significantly decreasing the computational cost of the subsequent multiaxial fatigue damage calculations. Moreover, it does so without losing the order information. That's the most important feature in fatigue damage calculations. Do not try to filter your signals using any frequency device filter. Anyone you try even the most modern wavelength-based systems do not work in practice. They distort the signal. And the racetrack filter does not. It preserves all the peaks, the major peaks and major valleys in the sequence they do occur. So we can do sequential fatigue damage accumulation. In this work, we are introducing a pre-processing partition system, partition algorithm, that optimizes the filter process, decreases significantly the time needed to filter a real history. Extremely fast, highly improves the output of the subsequent multiaxial racetrack filter procedures, preserving all the original low path shape and using a minimum number of samples for a given filter amplitude. And as I said before, we are willing not only to share these ideas with you, we are willing to share the code if you want. I do understand that programming is a skill, and we have done that. And we decided we are going to give the code to anyone who wants to use it. That's all.